Hi everyone. So as you can see before your screen now, I have shared the screen, so hopefully it's visible to you. I had forgotten to give these couple of exercises to you at the end of the last module. So these are two exercises where you're required to check for the causality of these two systems, right? So you should verify for yourself if these two systems described like so, where Y is the output and U is the input, whether these two are causal or not, all right? So I leave you with those two assignments. Maybe you add them up, those two exercises rather, not assignments. So you add them up with the exercises I've given at the end of the last module. And now we resume the content that we were supposed to discuss in this module, that is Laplace transform. Okay, so we stop the video and start. Yeah. So I am assuming that you are familiar with Laplace transforms and you've undergone a course in which you've seen what Laplace transforms are like, their properties are, yeah, and you know what the definition of a Laplace transform is. So this is a one-sided Laplace transform. It might appear as if I'm making too fine a point, I'm putting too fine a point on this 0 minus, but it is actually important. Yeah, so 0 minus means basically just epsilon to the left of 0, okay, where epsilon is a very small quantity, okay. So why this is important will be clear when we look at the precise descriptions of certain theorems known as initial value theorem and the final value theorem. Anyway, so I'm assuming that you are familiar with these definitions and properties of Laplace transforms. If you've forgotten, I'd encourage you to go through these properties. I believe you've undergone a course very recently in which you've come across Laplace transforms. So of course, as you might be aware, though this is the definition of an inverse Laplace transform, this is really not the way in which you obtain the actual inverse Laplace transform, okay? There are lookup tables. So you basically employ the techniques of partial fraction expansions, right? Okay, so although I said that you're familiar with most of these properties, I will still revisit them. And that's not just because I want to refresh your memory, but because I want to give you a system theoretic perspective, a control theoretic perspective, the way we shall be using it in this course. And that is why I shall be presenting the material which might appear familiar to you. You might have seen it in some other form, but nevertheless, I shall present it to you in some other form here. Of course, not all of these properties, because many of these are quite straightforward. For example, to verify linearity. So you can take these up as exercises as well, okay? If you remember them, well and good, just take up an exercise book and a pen and see if you can quickly derive these. If not, then go through the materials that you have from your previous courses, all right? So linearity, then this is a delay, yeah, a shift operator as we described in the previous module. This is the derivative, the Laplace transform of the derivative. This actually comes in handy while not just evaluating or deriving the initial value theorem, but also when you want to apply this Laplace transform in solving differential equations. Yeah, not just this, but also the Laplace transform of higher order derivatives, higher order time derivatives of functions. Yeah, so if you want to get a quick glimpse of these are there in chapter 2 of Norman Nice's book. It's given in a table, so it really doesn't make sense to reiterate them and write them down again, which is why I have them here in these slides. Okay, a very important property is this convolution. Okay, so as it's commonly said, convolution in the time domain is basically multiplication in the frequency domain, and the other way around also it holds true. So basically, convolution in the time domain, in the frequency domain, is tantamount to multiplication in the time domain. Yeah. Then there is something called the Dirac delta. So this is, although this is called a function with an abuse of notation, this delta is not really a function, in the sense that when you think of a function, what you basically think is that there is a domain and there is a range. So you pick up elements from the domain of the function, and for every element in the domain of the function, you assign a particular value in the range. Yeah, that becomes the range. But that is not how a Dirac delta is defined. Okay, a Dirac delta is defined with respect to how it acts on other functions. Okay, So in that sense, it is not the typical function that you encounter. In fact, it is a distribution in the strictest sense of, in a mathematically strict sense. Yeah, I wouldn't really call it a function, but nevertheless, most of your undergrad textbooks get by pretty well calling it a function. Yeah, just a fine point. Doesn't matter if you don't recall this, but it's good to know. All right, then comes this initial value theorem. All right, and this is the final value theorem. So the initial value theorem has this restriction that the LHS should exist. Yeah, so basically this limit should exist. Yeah, if this doesn't exist, then it doesn't make sense to talk about this. Of course, there are still ways of manipulating this. Maybe we'll cover this in later lectures, but in general, if there are impulses and their derivatives, so impulses means the Dirac delta, the derivatives are like doublet functions, triplet functions, and other such distributions, as we call them. Yeah. So when those are present, then generally this may not exist, this limit. And if that limit doesn't exist, then we generally refrain from using the initial value theorem, although there are ways of doing it in a sort of a brute force manner in some sense. It's a clever manipulation, but typically we don't use it. Then the final value theorem. For the final value theorem, of course, you need to ensure that this function, this f of t in the time domain, it neither diverges nor oscillates, because if it oscillates or diverges, then there's no point in talking about the final value, right? As you keep increasing t, if it's unbounded, the value will keep increasing. So there is no final value to which it settles. So if you find some Laplace transform, yeah, fs in the frequency domain, for which the corresponding ft is such that it is a divergent function, you might still evaluate this limit, yeah, but that is not meaningful in the sense that it does not say anything about what the final value is, because the final value is non-existent in such a case. All right. So these are some of the important properties. Then this is exponentiation, complex shift as it is called. This is basically a it's a shift in the frequency domain, in the S domain. All right. And this is of course time scaling, which by now you might have seen in the context of some of the exercises I've given you, like, y of t is equal to x of 3t, so on. That's sort of a time scaling is what we call it. Okay, and now we have some common Laplace transforms. So just as I gave you the analogy when you have log tables and anti-log tables and things like that, so also for Laplace transforms you have a lookup table. But with practice, you don't really need to always consult the lookup table for some very common functions, such as the step, the ramp, the exponential, the sinusoid, the decaying or the kind of divergent sinusoid, and things like that. For all these functions and many more, you'll gradually have them committed to your memory. With practice, of course, you don't have to go through the effort of memorizing. It happens with practice that you'll remember the relation between the time domain function and its corresponding Laplace transform. Right? So, that being the case, let me just take a while to okay, stop sharing this. I'll share these slides with you, so don't worry about it. Let me now go back to the, yeah. Okay, so, all right. So this is basically a content that should be part of the previous module, but I forgot to add this. So now we start this module here. So in case you're watching this lecture, I'm hoping that you'll watch this lecture after I have uploaded all the material, so you'll have the slides. So you're free to consult the slides. So I want to just talk about certain special functions and their Laplace transforms, which should be very apparent to you if you have the slides in front of you and those properties of the Laplace transform. Nevertheless, I urge you to actually revisit Laplace transform if you don't recall much of it. Okay. So first thing that I'll take up is the unit pulse function. Okay. So here's what it looks like. Okay. So this is, let's say, t0, and this is t of t is equal to 0, yeah, and this magnitude is unity. So let's say this is f of t, okay. So we describe f of t like so, is equal to, let's say this is how I define the unit step, okay. Unit step, there are different nomenclatures, by the way. So some use the notation u for a unit step. I'm using 1 for it, okay. So what is a unit step? Unit step is basically, you know, this particular function, sorry, this particular function, it looks something like this. So it starts at, there's a jump discontinuity at t is equal to 0, and then it holds the value unity. Although this doesn't look like a straight line, trust me, it is. Yeah. So this is the unit step. So basically, this is how the function looks. Yeah. If I want to explain this further, this is how it will look. It is 0 for all t less than 0. It is unity for t between 0 to t0, and again 0 for t greater than t0. All right. So now if you want to find out the Laplace transform of this, again, you can use the classical definition of a Laplace transform, or you can just, you know, use the knowledge of the fact that Laplace transform of the unit step is actually nothing but 1 over s. Anyway, so this essentially, I leave it to you to work out the details, and you'll find that this is nothing but 1 minus e to the power minus st0 over s. All right. So this is the unit pulse. There's a reason why I'm doing this. All right. And will be clear shortly as to why I'm doing this. Because the next important function that I shall be considering here is the delta function. Okay, not yet the Dirac delta, about which I've spoken a few extra words, you know, as in to clarify that it's not really a function. But this is a delta function, okay? For all practical purposes, this qualifies as a function, and it can be described by its behavior like so. So let's say this is what it looks like. Yeah, the height is 1 over delta. This is at some t, and this is at some t plus delta. Okay. Okay. So the way I define this this particular delta function, it has a width of big delta. There is this width is big delta, and a height of 1 by delta. So the area is unity. Okay. So let's just call it this by this notation. Yeah. Let's just say this is T1 and T1. All right. Yeah. So T minus T1 is equal to, now that you already know in the previous slide how we have defined this, yeah, this should seem very familiar to you now. So what is this? Oh, okay. So this is nothing but 1 times T minus T1 minus the unit step starting at T minus T1 minus delta. Okay. Why does this work out, by the way? I did not elaborate on this. So you see, this is with a positive sign. So this starts like this. And if you look at this other function here, this other unit step here with a negative sign, this fellow will start here, right, at T0. So therefore, the sum of the two is basically the resultant, that is this. Yeah. So by the same token, we are describing this particular delta function in this fashion. Okay. Again, you can describe it in the conventional notation like this. But I'm again, if you're interested, I'm leaving that as an exercise to you, right? So it has the following properties. First, that it has a unit area for every value of delta, because that is how it is defined, right? It has a height of 1 over delta and a width of, height is 1 over delta and the width is delta. So it has a unit area. The point is that as delta tends to 0, this is said to approach the Dirac delta. Yeah, it's like an impulse. So when, for example, a cricketer hits a ball, the impact between the bat and ball lasts for a very small amount of time. Of course, it is still a non-zero amount of time. So for all practical purposes, these kind of ideal deltas or impulse functions don't exist. Yeah, you can think of it as some sharp, some very high value of this particular function over a very small interval, so that the area is still finite. Yeah. So anyway, the point is that as delta tends to 0, this approaches the Dirac delta function. And moreover, in the limit delta tending to 0, the Laplace transform of this function, yeah, delta of t minus t1, is e to the power minus s t1. Yeah, I leave that to you as an exercise to verify. It's really not very difficult if you know the Laplace transform of these two, which of course we have shown you here. Yeah, in this particular case here, this is the Laplace transform. So you just apply that same principle here with the delta outside, and if you just apply certain rules of limits, you should be able to see. So this is also an exercise for you. So as a part of an exercise, show this. Okay. Yeah. So with that, now we will see some interesting properties of this delta function. One of them is the shifting property. Not the shifting, it is the sifting. That is a sieving, picking up, okay, filtering. So what does the shifting property say? The shifting property says, and this is exactly the way in which this is defined, okay? That's why it's a distribution rather than a function, okay? So for any function f of t, yeah, is nothing but, so it picks out, it sifts the value of the function at t is equal to t1, okay? So this is in fact can be treated as a sort of a definition of the Dirac delta function, okay? So of course, if you have defined it as I have shown here in the limiting through this limit, then you should be able to prove this property, okay? So that also you should try to take up as an exercise, okay, and show that this is true. Of course, these are there in standard textbooks, so you can also consult them in order to prove these results. But I'm not going to really derive all of these results. The next thing that I'm going to do is, again, please note I'm going quickly over the Laplace transform, the nitty-gritties of Laplace transform, except for the very important results. So the next thing before we move into something more interesting is, I just want to dwell a little longer on this initial value theorem that we had there, all right? So if you see that the initial value theorem, if you apply on this, yeah, this is basically nothing but the Laplace transform of the derivative of f of t, all right? And by definition, from one of the properties. Of course, this also you should be able to derive, but this is one of the properties that we showed you in the slides. So we can take this as true, all right? Now, excuse me, the point is that this part, this left-hand side, we can rewrite as sum of the integral from 0 minus to 0 plus this plus 0 plus to infinity. The same. So the integrand is basically this. This is what I'm putting in this bracket here. Yeah. Now clearly, this is nothing but yeah. Why so? This is nothing but f of 0 plus minus f of 0 minus. Because within the neighborhood of 0, notice carefully that e to the power minus st is basically unity. So it's basically the integration of f dashed, that is the derivative of f with respect to time. Therefore, this is what it turns out to be. Plus the remainder, let me write it down here now, infinity f dashed t e to the power minus st dt. Okay. So now this is 2. So the left hand side is equal to this, and that is also in turn equal to this. So combining 1 and 2, what we can write is that f of 0 plus minus f of 0 minus plus this particular integration is equal to s f of s minus f of 0 minus. So of course this and this will cancel out from both sides. Therefore, what we have is s f of s minus f of 0 plus is equal to this integration from 0 plus to infinity, integration from 0 plus to infinity, f dashed e to the power minus st dt. Now, if you pass this through the limit, yeah, this term is independent of s, so taking the limit does not affect this. This is where the limit will be applied. But if you apply the limit on this, notice what happens. F dashed is independent of s. If you apply the limit on this, you can interchange the order of the limit and the integral, and you push the limit inside. So therefore this, yeah, this takes it to 0, right? If s tends to infinity, this goes to 0, right? So as s tends to infinity, this goes to 0. So therefore you deduce, now I'm writing this in a very sketchy fashion, you should write it more clearly and convince yourself that this is indeed so. Of course, just a minute. Okay. Sorry about that. I think okay. I hope I haven't lost much of it. Okay. I'm not sure why I lost that screen, but let me share the screen again. Okay. Right. Okay, let me start writing here. Seem to have, the system seemed to have crashed. Anyway, sorry about that. Yeah, so where were we? We were actually talking about the initial value theorem. So in summary, in summary, we can say that limit s tending to infinity s f of s is indeed is equal to f of 0 plus. So that's why it's important to make the distinction between 0 plus and 0 minus. It's not something that you should be trifling with very loosely. Yeah, that's why I wanted to clarify that. Right. Now next, what we're going to do is we're going to see how you represent a signal as a sum of delta functions. Okay, let me just draw a sketch first. Let's say this is the function, and just a minute. Yeah. Suppose this is the function, okay? And you split this up. Yeah. Reminds you of something, right? Reminds you of the way you did Riemann integrations in some sense, right? Okay. So you split it up in this sense, right? So let's say this is T0, this is T1, so on and so forth. This is Tk. All right. So this is the time axis, and this is your exact function. Now, not y. Let me just call it u. Yeah. So the exact function is the one I've drawn with bold black lines here, and you're trying to sort of discretize it in some sense and get an approximation of this function here in this fashion. All right. So what are these functions? If you look carefully at these functions, these are nothing but those pulse functions, right? These are just pulse functions, just whose magnitudes are modulated. Yeah. So each individual pulse, what is it given by? If I write this like this, wouldn't you agree that each individual pulse, that is, say for example, a pulse like this, after all, what is this pulse? If I just write this as u delta ti, what is this pulse? It is nothing but u of ti, that is the value of u at ti, we hold it constant, times that erstwhile function that we defined, you remember? T minus ti times delta, okay? Where delta is nothing but ti plus 1, or rather ti plus 1 minus ti. So I can be anything here. Yeah, this is a particular I that we've chosen, but okay, let me call it k then. T of k plus 1 minus tk for any value of integral value of k. Yeah, so this is basically the spacing between the two. All right, so I can approximate this small pulse here in this fashion, this function modulated by this magnitude. Yeah, see, otherwise this part has a magnitude 1 by delta. When multiplied by delta, it has a magnitude unity. Yeah, the value of this function unity, and then it's further multiplied by u of ti. So that's exactly what the value is, right? So where delta of t minus ti times this delta is a pulse of unit amplitude. All right. Now, therefore, an approximation, let's say u bar, this is an approximation of u bar of t can be written in this fashion. I is equal to 0 to infinity, u of ti, delta of this t minus ti times delta. Yeah, this is an approximation. Nevertheless, if you understand what we're going to do next, we're going to assume that this delta becomes very small so that this approximation error is minimized. All right. So when delta becomes very small and is almost tending to 0, this basically reduces to an integration. Yeah. So what this then reduces to is the following. We can then say that this u of t is nothing but limit delta tending to 0 summation. So the approximation error goes to 0 as delta goes to 0, right? But I is equal to 0 to infinity u of ti delta of t minus ti times delta, which can then be written in this fashion as the integration from 0 to infinity u of tau delta of t minus tau d tau. Yeah. So this is how you can approximate a function, right? Using the Dirac delta. You can actually achieve an expression for the function using this Dirac delta. All right. So why are we doing all this? Yeah. Because remember, our ultimate goal is to see that when you have this input ut and you apply this to a linear time invariant causal system, which is characterized by G and which gives an output yt, we want to find out how this y and u are related. All right, what special benefits can be harnessed through these properties that we have imposed on this system G. Yeah. All right. So having come this far, we will assume, let's quickly write down, G is linear, time invariant. Okay, we'll bring the causality later. Let's leave it for now. Linear, time invariant, and it is initially relaxed. What I mean by that is that whenever, whatever you choose as your frame of reference, that is 0, yeah, before that 0, t is equal to 0, the value of this is 0. All right, so it is initially relaxed. So all the initial conditions of your system are 0. All right, so these are some of the assumptions we make: linearity, time invariance, and initially relaxed. Okay, now what then would be the y? So y would then be given by G acting on this sum, right? G acting on this sum that we had so carefully written just a while back, right? So we pull it out of the hat again, rekindle this t minus ti times delta. Okay, now we one by one we bring in these properties. Since it is linear, therefore additivity and homogeneity hold. So remember that this is just a scaling factor. Yeah. So therefore we can write this expression as what? We can pull it out, we can pull out the delta outside. Yeah. And we can write this as I is equal to 0 to infinity G of u ti delta of t minus ti. This is due to the linearity property. All right. What happens next? What happens next? Look, what about this uti? Isn't this also a constant? The way we have drawn this, these are all constants, right? So it's a constant scaling. So we can pull out this uti also outside of this bracket. So therefore, we can write this quite simply as summation I is equal to 0 to infinity G of u, sorry, not u, quite simply as, yeah, just the delta remains inside this, t minus ti u of Ti times delta. Yeah. What is the specialty of this? Why did we strive towards this? What is the point of everything that we did so far? Yeah. The point is that now if you let this delta tend to 0, now this reduces to the integral. Also, we shall now bring in the time invariance. And why is the time invariance critical at this juncture? Look, we have used the linearity property to push in this G inside the summation. Yeah, that was because of linearity that we were able to do this. Now, how are we going to use the time invariance? The fact that this, let's turn our attention to this term, G of delta of T minus Ti. Yeah, what is this? This is basically response or output of the system at time t due to the application of the input delta at time ti. Notice that this response depends only on the difference between these two time instants. Why? That is because of the time invariance. Okay. Otherwise, for every pair, okay, so if you want to find out the response or output of a system at time ti due to an input applied at time tj, you generally denote it as y of t, sorry. Uh-oh. This is bothering me now. Okay. Okay. Sorry about that. Once again, this file closed. Hopefully I haven't lost much. Yeah, thankfully we haven't lost much this time around. Okay, so let me share the screen again. Yeah. All right. Yeah. So basically what I'm saying is that when you write this G of delta of t minus ti, it is basically the system's response at the time instant t due to the application of this delta at the time instant ti. Okay, and it only depends on this difference t minus ti. If this were a time varying system, then it would depend on the instant when the input was applied and the instant when you are looking for the output. Okay, because here whether you apply an input at the 5th second and look at the output at the 10th second is the same as whether you apply the input at the 105th second and look at the output at the 110th second. Okay, because the system does not change over time, so it's only the difference between the instant at which the input is applied and the instant at which you're observing the output that matters. In layman's terms, essentially that is what it is. All right, so now the idea is, the point that we are trying to drive at is that we may write this yt as the integration from 0 to infinity. As delta tends to 0, we may write this as g of t minus tau r tau d tau for t greater than tau. Okay, where now by the same token g of t minus tau is called something, it's got a special name, that's called the impulse response. Why? because it is the response, impulse response of system at t due to delta t minus tau applied at tau. So this is the impulse response. Okay. So for a linear time invariant system, it's a very important parameter, this impulse response, so defined. Okay, in the time domain. It turns out that this impulse response has a very important role in whatever we're going to do next, because in the Laplace domain, the Laplace transform of this impulse response happens to be the transfer function. So that is how it's defined. Okay. We'll see more details of this. For now, it just suffices to know the name. So this is the Laplace transform of the impulse response. All right. So now, one by one, we have applied those properties. We have seen why they're important. So we have written y of t is equal to integration from 0 to infinity g of t minus tau u tau d tau. Okay. I now impose the condition of suppose system is causal. Immediately you will see that I can write this as, due to this causality, I can write this as 0 to t, why? It's very important to ask these questions, why? Why? Because I am looking at the output at the time instant t. Obviously, if it is causal, it cannot depend on any input that is applied beyond the time instant t. So therefore, it should not care about whatever values t takes, this ut takes. If I had truncated this ut, it would not matter. So let me truncate u tau beyond t, right? This u tau, tau is the running variable. So let me truncate this input beyond the time instant t. If that is so, then basically I'm multiplying this by 0 for every value of tau greater than t, which is the same as taking the limit from 0 to t in this integral. So if this is, in addition, this is causal, then this is how the input and the output are related, where this G is the impulse response. So if someone gives you the impulse response of a system, of a linear time invariant system, they've given you everything that you need to know in order to be able to solve for the output of the system for a given input, in theory. Okay? But of course, things are not as simple as they appear. So this is known as the convolution integral. Okay, this is known as a convolution integral. Exercise, I urge you to show that 0 to t g of t minus tau u tau d tau is equal to 0 to t g of tau u of t minus tau d tau. It's very simple, and you should be able to derive this on your own. All right. So the next step that we're going to do is, now we are going to look at the Laplace transform of the output. Okay. So far, what have we done? We have got a signal. We've broken it down as a train of pulses, sum of the pulses, and then we've shown that as the limit delta tends to 0, it goes to an impulse. It goes to an integration, like so. Yeah. I'm sorry about that. The slides in between have vanished. I'll have to rewrite them. Yeah. So this is what we essentially did, right? This is what we have done with the system, and eventually we've arrived at this. Okay. Now, what about the system output in the Laplace domain? Okay. Because we know that the input can be very well written down in simple terms in the Laplace domain, right? Because we know at least the approximation of this input, we know what the Laplace transform of this is going to look like. Yeah, the sum. It's going to be an infinite sum, but we know what this is going to look like. So what about the Laplace transform of the output? That is what we're going to seek next. Yeah. Okay. So the Laplace transform of the output. Okay. Let's quickly write that down. And so this is nothing but Laplace transform of 0 to t, g of t minus tau, u tau, d tau, right? And if you have already proved in the previous exercise that I've given you, you would see that it is nothing but g of tau, u of t minus tau, d tau, all right? And now we can write this as, pay very careful attention to this. We're going to again go back to this. Why? Every time we do some such manipulation, we must ask ourselves why we are allowed to do this. So why am I going beyond this? Because I'm arguing that u of t minus tau is equal to 0 for all tau greater than t. Why so? Sorry, this u has somehow vanished. Yeah. So I'm arguing since u of t minus tau is going to be 0 for all tau greater than t, therefore I might as well extend this integration from 0 to infinity, and it will not matter. It will not make any difference. Why is this true? What am I bringing in now? What assumption did I make earlier that is enabling me to do this? Why is u of t minus tau going to be 0 for all tau greater than t? So if you look at this, function, let's say, let me draw the sketch here. If this is u of tau, if this is u of tau, is the tau axis, tau is the running variable, then this is u of minus tau. Yeah. And now, if you shift this, yeah, like so, right? So therefore, this is u of t minus tau, right? So if this is u of t minus tau, you can clearly see that the assumption that the system, that the input and everything is initially relaxed, yeah, because of this initial relaxation, this condition holds, right? So that is why we can as well extend this, right? Okay. So now we write this Laplace transform and it will be another integral. Okay. So we put another integral 0 to infinity, and then maybe we put this other integral 0 to infinity, g of tau, u of t minus tau, d tau. Then this is dt. Of course, you have to have e to the power minus st because of the definition of the Laplace transform. All right. What does that lead us to? That leads us to L of yt, that's the output, is nothing but yeah. So we might as well write this as 0 to infinity. Let us change the order of integration now. We'll change the order of integration and we can write this as g of tau, u of t minus tau, e to the power minus st, and we bring the dt inside and the d tau outside. We change the order of the integration. All right. In the next step, we just give the same thing here, g of tau u of t minus tau e to the power minus s tau times e to the power minus s. Now we write t minus tau. Okay, so we're just adjusting this here. All right, and then we write dt d tau. Right? Then we write this as 0 to infinity g tau e to the power minus s tau. We pulled it out together here. And now this 0 to infinity u of t minus tau e to the power minus s t minus tau dt and this d tau. All right. Now what we do is we split this part up. We split this up into two parts. This is g of tau e to the power minus s tau. We split this integral up from 0 to tau plus tau to infinity. Okay, and then we have d tau outside. The claim is, the next claim I'm going to make is that this part is going to vanish. Okay, why so? This part is going to vanish. Why is this part going to vanish? This part is nothing but this integrand from 0 to tau. Why is this part going to vanish? Because now we will write that r of, sorry, not r, it's u we have written, right? Yeah. This part is going to vanish because again we use the same argument, but this time reverse, because this time we are using the argument in t. So u of t minus tau is equal to 0 for all t less than tau. Yeah. Uh-oh. That was I. Okay. All right. So having done that, what we then get is that the Laplace transform of y of t is nothing but this integration 0 to infinity g of tau e to the power minus s tau, and within the bracket by a change of variables now. Yeah, so what we are left with is basically this tau to infinity u of t minus tau e to the power minus s t minus tau dt, right? Because the second integral, as we've argued, vanishes. Now this we name t minus tau as a new variable, let's say some beta or gamma or whatever you call it. And again, fill in the step in between. This is an exercise. You'll eventually get 0 to infinity g tau e to the power minus s tau d tau times integration 0 to infinity u of gamma e to the power minus s gamma d gamma. Yeah, and that is nothing but g of s times, sorry, what was that, times u of s. And what is this? This is the Laplace transform of the impulse response, like we had claimed earlier. So what happens is, notice very carefully, although towards the earlier modules of this lecture we have seen, we've operated this g, yeah? We operated this g on some u. Notice that this wasn't a product, yeah? This was just the operation of g on u, okay? But it turns out that in this Laplace domain, or in this frequency domain, for a linear time invariant system, the action of a system on an input signal is captured by multiplication. So basically, if you want to describe this succinctly, the Laplace transform of the output is nothing but the product of the Laplace transform of the impulse response and the Laplace transform of the input. This Laplace transform of the impulse response is what we call the transfer function, and is a very important thing that we'll encounter throughout this course, the transfer function of the linear time invariant system. Okay, so it's convolution in the time domain leads to multiplication in the frequency domain. We've actually proved that here. All right. Okay. So now that we are through with this, before we close this particular module, I'd like to take you back to the ordinary differential equation that we had described towards the beginning of this lecture in one of the earlier modules. Yeah. So let us suppose, you have this a0y triple dash plus a1y double dash plus a2y dash plus a3y is equal to b0u double dash plus b1u dash plus b2u. All right. Now that you know what to do with this Laplace transform, how to do this Laplace transform, I urge you to go through the table, Norman Nice's book. Assume the initial conditions to be 0. That is, the system is initially relaxed. All right. So if you assume that the initial condition is 0 and the system is initially relaxed, you will see that if you take the Laplace transform, taking Laplace transform on both sides, what you will then arrive at is as follows: a0 s cube plus a1 s square plus a2 s plus a3 times y of s is equal to b0 s square plus b1 s plus b2 times u, times u of s. All right. Okay. So once you have done that, what you may then write is the following: y over s upon u over s is nothing but summation bi s to the power. Okay, I mean, this is not a general expression, so let me write it's only got a few terms here, so let me not go for this overkill here. Yeah. So basically, this is nothing but b0s square plus b1s plus b2 over a0s cube plus a1s square plus a2s plus a3. Yeah. This is what this expression turns out to be. Okay. And this is indeed the transfer function of this system. How do you know that? Yeah, the question arises, how can you verify that this is indeed so? Look at the definition of the transfer function. The transfer function is nothing but the Laplace transform of the impulse response. What is an impulse response? An impulse response is that output which is obtained when the input is an impulse. So therefore your u has to be the impulse. Okay, so therefore if you reduce this us, if u is an impulse function, then what is us? us is nothing but unity by definition, right? I urge you to again revisit that slide so you know that the Laplace transform of the impulse is indeed unity. So therefore this becomes unity. So then what is your output? This y then becomes the impulse response, right? So therefore this, for an ordinary differential equation, linear differential equation such as this, an alternate definition of the transfer function is that it is the ratio of the Laplace transform of the output to the Laplace transform of the input when all initial conditions are 0. Yeah. So it is basically the ratio of the Laplace transform of the output by the Laplace transform of the input with all initial conditions set to 0. All right. So that is another way of seeing this. Typically for physical systems, I might add transfer functions for physical systems are at most biproper. What do I mean by that? You see, there's a polynomial. In this case, it's a quadratic polynomial in the numerator and a cubic polynomial in the denominator, right? So it's a rational function. GS is a rational function in S. Okay, is given by GS is equal to NS over DS, where NS and DS are both polynomials in S. Yeah, in the variable S. All right. So the degree of n, suppose, is m, and the degree of d is suppose n, then n is greater than or equal to m. If n is strictly greater than or equal to m, then it is strictly proper transfer function. If n is equal to m, it is biproper. What happens if they're improper? What happens is that you will encounter impulses. Okay, so for an input that is bounded, or let's say an input that does not contain any impulses, you will encounter outputs that might have impulses. All right. Why is that? Take the very simple case of transfer function given by, let's say, S. Suppose GS is equal to S. All right. What happens? Suppose you give an input 1 of t. Okay. So suppose this is your input 1 of t. Yeah. What is then the output of the system? Yeah. The output will be nothing but, so this is basically the Laplace transform of 1 of t is nothing but 1 by s. So therefore the output will be the Laplace inverse of s times 1 by s, which is nothing but the impulse, right? So this generally doesn't happen. That's why all physical systems are generally strictly proper or at most biproper. All right. Certain other important things here. Another definition, and then we'll close this module for today. So roots of ds are called poles of the system, and roots of ns are the zeros of the system. So basically we can characterize this linear time invariant system by its impulse response, in turn also by its transfer function, because the one is related to the other through a Laplace transform, right? And when you have already gotten the Laplace transform of the impulse response, which is the transfer function, then basically the system can be completely characterized by its poles and zeros, because what else do you need in order to characterize a polynomial but its roots? Yeah. So therefore the behavior, the overall behavior of a system can be studied if you understand where the poles and the zeros of the system lie, right? So with that, we will close this module and lecture number 1. In lecture number 2, we'll start to see how you can take inverse Laplace transforms. Of course, if you've already done this in your courses, as I'm informed you have, please revisit them. Then we shall quickly go over that, because there are a lot more things that we need to cover beyond what has already been covered in your previous courses. Okay. So I'll stop sharing the screen. Thank you very much. And with that, we come to the end of lecture 1. Please solve all the exercises. Thank you very much.